All right, so now we will be talking about the third reinforcement learning algorithm that's called reinforce. Now, in the reinforce algorithm, we will also be training a neural network. Okay, so in this situation over here, we have this model, okay, that generates the probability for taking a certain action at a certain state. Okay, so what does this neural network do? For example, you give it a certain state, okay, like for example, a certain state. Okay, let's say that the system is at certain state. Okay, so for any action, it will give you a probability. For action X, will give you, for example, point, point 1 or point 0.5. The higher the probability, the more likely we are going to take that action. Okay, so instead of kind of like talking about the Q values, here we are talking about something that's kind of like similar, but it's an absolute probability. Okay, so this model, we say, if we are at position X and let's say velocity Y, okay, if we are at a certain state, what is the probability that we will take action one, like for example, turn left or turn right or do nothing or anything? Okay, the model would say, point 0.1 or point 0.5 or point 0.6. So instead of dealing with Q values like we used to do in the previous two methods, here we are talking about absolute probabilities. Okay, so this is the basic principle behind the reinforce method. So for a first glance, assume that this is our neural network. What would be the objective function? All right, so right now I have this function, okay, which is the neural network of the action and the state. So whenever I get a high reward from the environment, I want the probability or this function to be high, right? And if I get low reward or negative reward, I want this probability to be low. So right now, how can I set up a loss function that will do this effect? All right, now this is how the loss function is going to look like. So how did we get here? And what is this exactly? First of all, we have worked with the log of the probability because working with the log of the probability is more stable than working with the probability directly. But if you get the maximum log, then probably you have gotten the maximum probability. Okay, so this is the first thing. So again, what are we doing over here? We want to set up a loss function that will eventually end up in the following thing, that it will generate high probability for the actions that generates high reward. Okay, so if the action at a certain state generates a high reward, we want this model to generate a high probability for it. Okay, so here's what we can do. What if we multiply the log probability generated by the model by the reward it has caused? And then after that, we adjust the weights, which is theta, in order to maximize this function. So this reward over here is actually a scalar. It scales the log probability generated by the network. So here is how this multiplication will actually um, uh, make this training process work. Okay, let's look at this function over here in order to understand why does this multiplication work. Okay, let's assume that our log probability function is like this. Okay, And right now we are here. Okay. So right now, whenever we try to using the gradient ascent method, which we will use, or descent method, okay, what the way we actually maximize this function by changing the weights is that we find the slot, which is like this, okay? And according to this slot, we make a step forward, okay, like this. Okay, so we move to this next point by changing the weight or updating the weight. So right now, whenever we multiply this function, this whole function by a reward, by the reward generated by this action, let's assume that it is a big reward and it's a positive reward. What will happen is that this is going to be the function, right? Because we have scaled it, we have multiplied it by a scalar. So everything is kind of like, multiplied right now. So, okay, what will happen right now is that the slope will increase, okay, because the function is scaled up. So right now we will have a larger slope, okay, and we will move more aggressively in the direction that will maximize the probability, because right now we have got an upscale function, right? Okay, another way, okay, that can happen is the opposite. Let's assume that this action has actually resulted in negative rewards. So we will multiply it by something negative, so it will turn into the other direction, for example. Okay. So in this situation, we will go in the opposite direction. Okay. So in this situation, we will go in the opposite direction in order to reduce the probability of taking that action. So right now, I've given you a very simple example on how multiplying by the reward or multiplication of the objective function by the reward has resulted in a function that will generate higher probabilities for for the actions that will generate higher rewards. So over here, the summation is that because we want to work among all the steps that has been taken throughout the episode, not just one step. So this summation is for all the steps that has been taken throughout the episode. So let's have the following simple numerical example in order to understand what's going on. But before we take a numerical example, I want to explain how do we evaluate this reward over here, because it's a very, very nice part of the algorithm. So let's assume that we are right now at time zero, okay? And we have taken a certain action, and that has generated a reward of one, for example, okay? And then at time one, we have taken another action, and it has generated, for example, a reward of 0.5. And then at time one, or time whatever two, has generated a reward of, let's say, 3. Okay. So right now, the reward at 0 is going to be the following. It will be the reward at 0, which is 1, plus the reward at 1 times gamma. Gamma is kind of like a reduction factor. Okay. Plus the reward at 2 times gamma squared. Okay. So this evaluates how good was the action which we have taken at time 0. Why? It's kind of like the example that we have talked about before, that the action you are taking right now will affect the efficiency of the future actions, because the future actions will be built upon that action. So if at this step you have selected a good product, for example, in a business, whenever you make an ad campaign, it will be successful. Okay, so it will be highly rewarding. Okay, and after that, maybe if you do customer support, it will be highly rewarding. Okay, but if you pick a bad product in the beginning, okay, the rest will not be rewarding because the initial action was bad. So it makes sense that we evaluate the quality of our action at time 0 by the results which we get at time 1 and 2 and 3 and 4. And this is how this algorithm works. Okay, so this RT is actually the accumulative reward based on that action until the end of the episode. Okay, so, and right now in the following numerical example, we will have a close look at how this works. So right now we have the following examples. Example, we assume that we have 3 time steps. Okay, so we have a certain system and we have made 3 time steps within that system, and we got the following reward. We got a reward of 1, of 1, of 1 at each step. Okay, just to simplify things out. Now, this is the discount factor that we have talked about. And our model has generated, okay, the following 3 probabilities, which are point 0.3, 0.7, and 0.6. Okay. So until this point, I think everything is clear. Now, this is how we found the reward for each step. So, okay, the reward for action 0 right now is the summation that we have talked about. Okay, the first reward times the gamma plus the first reward times the gamma squared plus, okay, etc. Okay, now for for the reward for time 1, this is how it's calculated. And for the reward for time 2, this is how it is calculated. So again, this is how we evaluate the quality of a decision based on the results of the next decision that was based on that decision. All right, so those are our final, we call them returns or rewards. Okay, so they call them returns. Okay, so right now, this is how we evaluate the loss at each time step. So at time 0, okay, we got the log probability, okay, times the accumulative reward, or they call it the return. At time 1, we got the probability of this action and the accumulative reward of this action. At time 2, we got this log probability and this reward over here. Okay, and right now, summing them up, we get the final loss over here. Now, one important thing is that in PyTorch, we use the gradient descent, which minimizes the objective function, which is, this is our objective function, right? Okay, let me remove this. Now, this is our objective function over here. Okay, so since in PyTorch we minimize the objective function, but we want to actually maximize it. So in order to maximize it, we just add this minus sign over here. So this is the secret behind this minus sign. Okay, because in PyTorch, the package we are using is actually minimizing. So it changes or adjusts the weights in order to minimize the objective function. And this is our objective function. Okay, so in order to get around this, we add a minus sign. So if we minimize the minus of an objective function, we're actually maximizing it out. Okay. Now, if you understood this example over here, okay, you will be ready to understand the code. So let's go right now and have a look at the Colab tutorial. All right, so this is our notebook, and this is our simple, feed forward neural network, nothing complicated, some linear layers, some activation functions. So this is our neural network that we will be training. Now, this is the function that calculates the accumulative return, or they call it the returns. As we have said before, R0 plus, gamma times R1 plus, gamma squared times R2, and so on and so forth. Okay. Okay, this is what it actually does. It's simple function over here. Okay. Here is where we initialize our network to train and define the optimizer. All right, now this is our counter over here. Now this counter is the one episode is one of the episode. Okay. This counter is for all for the episodes. Okay, so in this situation we have 5 episodes. Now this counter, while not done, will keep looping until the end of one episode. Okay. Now now this is the summation function that we have talked about. We have defined it into the loss. Okay, and then we send it to the optimizer. Okay. So this is uh, the loss function. Okay, and if you look closely at it, this is the accumulated reward that we have evaluated, and this is the log probability that we have talked about. So this formula over here is let me show it to you right now once again. Yeah, it's this function over here. Okay, the log probability times the return. They call it the return. Okay, at all the time steps. Okay, so this is the summation that we're actually talking about. So, for each episode, we will go through the steps until one whole episode is finished. Okay, and we will append and stack up the log probabilities among each time step, and we will also stack up the rewards. Okay, and then once we have a list of the rewards and the log probabilities, we will go here and plug them into the loss function in order to make the summation that we have talked about. Okay, just the log probabilities and the returns in order to evaluate the summation, which is at time 0 and time 1 and time 2 and time 3 and 4 and so on. After defining this loss, we'll go to the optimizer. Okay, and this optimizer will adjust the weights in order to maximize this objective function, which is minimizing minimizing this whole thing, right? Because if we minimize the negative of a function, then we are probably maximizing it, right? Okay. So this was the breakdown of the code over here. In our code, we have also applied the SVD to some layers of the neural network. And then during training, we just take the highest singular values that are higher than a certain number in order to smooth things out. So right now, let's run this code and look at how it works. Okay, first let's pip install those things. All right, so right now after running the cell, we will run this one that is with the SVD part. So I'll run it, see if we start learning. All right. Okay. So now we're applying the SVD by kind of like smoothing out some layers with the neural network. Okay. So right now seems like the reward is increasing, which is good. So we are improving. I don't know how many episodes we have. Okay. We're keeping kind of like the highest 10 singular values within the neural network whenever we apply the SVD. So right now we've got total reward of 500. I think maybe this is the maximum thing that you can have. So maybe it will stay at 500. That has improved nicely. I think maybe let's have a look at the system that we're actually training. Okay, I think we have reached what we want. I don't know how many. Okay, eventually it will generate kind of like a video, right? I think I've made it um, generate kind of like a video. I'm gonna find an episode and save it as a GIF. Okay, so it will generate a video of the last episode in order to see how the system is working. Um, let me see how many episodes do we have here. Um, we have 500. Okay, maybe we're gonna have to pause this because right now we are at episode 100. Okay. Okay, I'm not gonna wait for 500 episodes. Okay, let's restart this. Okay, and just train it for 50 episodes and have a look. But eventually, we have reached this kind of like high reward, which is 500. Probably it's the maximum thing like that we can reach. So I will um I will make it 50 instead of 500. And I'll run this instead of waiting forever. Boom. Okay. Um, okay. Okay, we're done here. We have reached, okay, very low reward. Okay, that's not good. But let's have a look at this at the system. Okay. Yeah. So this is the system. Okay, this is the system. And what the system is doing is trying to keep this card up for as long as possible. Okay. So I just wanted to show you the system. And it was clear that it was successful in doing that when we train it enough episodes. Maybe it was not able to do it right now in 50 episodes. Okay. So this is what we are trying to train. All right. I hope this was clear. Thank you for listening.